So in this video, I will explain how to extract T1 and T2 from your data. So this is a set of data from a certain type of oil, Pascal oil, and these are the delay time between the A pulse and B pulse. So the free induction decay, I already inverted the values before before this 0. And the rest were not inverted. So now this should actually be roughly an exponential curve. So that's right there, and I can hide the fit curve, so that this curve is also going to disappear. So this is my actual data. As you can see, these values were actually positive, so I added negative signs for them to become negative. And as they approach the 0, it gets a little less certain because the readout is lower magnitude. So we could actually ignore some of these if you want, such as these values, or even maybe more values, because they have higher relative uncertainty because they're lower magnitude in voltage, and our scope is not very good at low voltages. So this function is just going to be typed in literally right here. Sorry, not this one. Let's unhide. So you type in this function literally. This is that V0 magnitude, and apparently my voltage was lower. If you looked at my 2021 data already, I got a little better result with a different oil. So this voltage 0.58, and then 1 minus here 1 minus 2 exponential function of minus t over the t1. So t1 is a fit parameter, and the v0 is a fit parameter, and that's it. So the T1 are the delays in milliseconds, and T's are delays in milliseconds, so that means the T1 will come out as milliseconds. So all we have to do is to autofill all these, and then calculate the variance between the actual voltage and the fit voltage as the square of their differences, just like this, square of the differences. And then we'll calculate the sum of all those squares, SOS, sum of squares. So let's just say that we start maybe minus 0.55, and I think the oops, not minus, excuse me, positive 0.55, and maybe we start from the 25 milliseconds just as a guess. So okay, our guess is close enough to the data, and we have the sum of squares. So the rest we'll just let Excel solver do. So we select our objective, which is sum of squares, and we wish to minimize that by by changing these values. The values are H1 and J1, so V0 and the T1, and then we'll just uncheck that and do solve. Remember, this was 0.12, now it's 0.002, so that does minimize this, and you can see the fit is actually quite nice. So we solve the T1 to be 20.7 milliseconds. And from this year, this is my result from this year. It seems like there's a little more discrepancy here. Maybe it's just me having more data. Whichever is the case, you could, if you want, delete a couple of these data points close enough to the 0. The lower the magnitude, the lower the relative, the higher the relative uncertainty. Right? So you would actually just take this, and I did from 1 millisecond to 60 milliseconds. Apparently, I didn't have to do so many over here where changes are slight, but that's what you get from a different brand oil, a Squid brand oil. I did in 2021. So that's T1, how to calculate T1. So let's do calculating T2. So T2 we have peaks, and in here we only had a short number of peaks. So this is okay. So let's focus on these. So we have 2 milliseconds for up to 60 milliseconds. So there's a number of peaks, and then the signals are the signals of the maximum of each spin echo. And the function to fit, I don't know where that has gone. Okay, so let's see. So let me maybe just type up that fit function. Insert equation. So m xy function of time equals m0 times e to the minus t over t2. Okay, so now I should be able to precise this. Okay, so we're just fitting something relatively simple, exponential function that has one parameter, the t2, two parameter, the m0. So that's exactly how I did it. This is that m0, or the v0, the voltage, and then there's also a t2 here, right here. So I did the fit and also calculated the variance between the actual signal and the fit result and square that, and that tells me how good the fit is, and then I sum all those squares to get sum of squares. So then I'll just give these values and have Excel do the Excel solver do the fit. So this I can say, well, I started for 1.02. Maybe I missed some because I started from 2 milliseconds later. So I can give maybe 1.4 as a starting point. And time constant, well, in a few time constants, it drops down to that 20%, maybe 3 time constants away. Maybe I'll start with 5. So the blue dots are the data, and the orange dots are the fit. So I can have some starting point, and then I'll use Excel solver again. So I'll pick, well, I don't know what happened with those graphs. Okay, I was using this right here. So I'll pick, I need to reduce sum of squares, minimize that, and I have the voltage and also comma the time that I can fit with, uncheck that, and I can solve. Remember our SOS is 0.11, so after solving it has gone down to about 1,000th of the original value, so that gets you the T2. So that's basically how T2 is obtained, and with this year's data, I have a lot more data points, as you can see. But I also got rid of the t equals to 2 because it's just very close to the t equals to 4 milliseconds. So this should be easy enough to fit with an exponential decay, and then you can extract your T2 here. Here I have a couple different different columns because I actually did some saving of the screenshots, but I realized I probably was better off just picking the peaks from the screen. I described that in one of the videos of my experiments, so that's what I got from here. I didn't really go into the data sets to extract the maxima, which will take some time. Okay, so that is how to fit T2. These fittings are less difficult than the fittings you have done in the past. So hopefully this won't take you too long to get done. All right, thank you.